so that they'll join.
Okay, sure. Just give me a moment. So is my screen visible?
Yes, Sashank.
Yes.
Yeah, am I audible? Am I clear?
Yes.
Yeah, okay.
Yeah.
So let's start. So what is data pre-processing? Data pre-processing is a data mining technique which involves transforming raw data into understandable format which like the model can understand. So as you can see, the real world data can be like incomplete and have a lot of anomalies and data errors, inconsistencies. So basically, the real world data won't be like perfect as you think. So data pre-processing methods have been proven to be like to improve the efficiency of the model and to improve the model's performance. So why do we need data pre-processing? So as I said, real world data can be noisy. So poor data leads to poor model building. So like poor quality of collected data further leads to low quality of models built on such data. So in order to overcome these issues, data pre-processing provides set of a lot of operations which can organize the data into proper form, and it organizes data in such a way that the model can understand and build. So what are the techniques that we're going to use to pre-process the data? So there are four main methods of pre-processing data: data cleaning, feature engineering, feature scaling, and data reduction. So we're going to look into these four topics one by one and see the implementation of those topics for each type of data set. So let's move on. The first thing, data cleaning. So data cleaning is a routine which uses the attempt to fill in missing values and smooth out the noise while identifying the outliers and like handling the inconsistencies in the data. So as I said, data can be noisy and have incorrect, even have incorrect attribute values. So owing to the following, um, the errors in the data might be from humans, like humans misinterpreted and entered the wrong value of the data, or transmission can also occur, and failing to record the data, so unavailability of the data. So dirty data, also known as like noisy data, can cause confusion for the mining procedure that we are about to do right now. So in order to like build good model, data are always not robust. So we need to pre-process these data and create data in such a way that model can build, as I said. So these are some of the basic steps you need to follow in order to clean the data. So first, looking at the data and to see how many missing points or missing data we have, and figure out why the particular data is missing, and to decide whether we can drop the missing values or fill the missing values. So let's see the implementation. So today I'm going to be using two different data sets. One is NFL. NFL is a sport played in America. So you might have heard like they call it the football in their country. And another is San Francisco building permits. So each block, the permit of each house. So we're going to be looking at these two data and trying to fill these missing values and trying to correct the data. So I've imported pandas and numpy to help us. And this np.random.seed is nothing but every time when we run random samples, it always produces the same results. So no matter what number you set the seed, it's gonna always produce the same results. That's the purpose of me setting the seed. Nothing else. So let's take a look at the data and see how many columns and how many records that this NFL data has. So a quick check reveals that we have like 102 values from this data. So this dot sample from pandas gives us any 5 random samples from the data and gives us the data. So just by looking at the data, we can already figure out that we have like 2 missing values here, and like we have missing values here also. So let's see how about we can go and overcome these issues. And this is final data. Now let's look at real life observations. The same thing I did for San Francisco permits also. I took the samples, any random five samples, pick data set, and we can see we have a lot of null values here also, like street number suffix and existing construction type has a lot of null values, and it goes on. Not putting a lot of null values. So we're going to use isNA function from pandas. So what it returns is it returns a Boolean value, whether in that particular cell we have the null value of true or false. False meaning
Excuse me, Sashank.
there is no null value present in that. Yeah.
Sashank, it's
can hear
your
you.
voice is breaking.
Is it clear right now?
Yeah, okay.
Hello?
Yes, Sashank.
Clear, right? Should I explain it from the first, or you missed something? Should I explain it from wherever
No,
you
you
missed?
can continue.
Okay. So, as I said, in order to understand the data better, we will look at the total number of null values present in each column of this NFL dataset. So, in order to get that particular result, we'll use SNA function from Panda. So, what it does, it returns a Boolean value for each cell. So, naming false meaning the particular data has no null values, and true being it has null values. So what I did was get the Boolean value and sum it up and get the total number of null values in each particular column. So a quick operation reveals that this down column has over 60,000 null values, and yeah, a lot of columns have a lot of null values. And this is just for the first 20 columns, because I can't display the whole 102 columns here.
Excuse me,
So
Sashank.
the first 20 columns itself has these many null values.
Sashank,
So now
can you hear me?
I can hear you.
Hello, Sashank.
Yeah, I can hear
Can
you.
you please check your networks, Sashank?
Hello? Am I audible right now? Is it
And
clear right
one
now?
more thing, can you please increase the font size also?
Hello?
Just go to full screen mode.
Is it okay right?
Yeah,
Am
yes,
I
okay
audible?
now.
Firstly,
Yeah,
am I audible?
okay now.
Is it clear? Okay. Is the font size also
Yes,
also
you're
legible?
clear now.
Can you read these words? Okay. Yeah.
Thank you.
So let's look at the total number of percentage of null values we have in total data set. And what I did was, as I said, I multiplied rows and columns, got records, and we already calculated the total number of sum of null values data set and multiplied by 100 to get the percentage, which is 25%, and almost quarter of the cells in the data set are empty. And we're going to look at some of the columns with missing values and try to figure out what might be going on with them, so why they are missing, and figuring out methods to overcome these issues. Before that, let's take a look at the same type of example for San Francisco permits also. Same, the first 20 columns I got. So for this data set also, number of columns has a lot of missing values. Like this column has over 2 lakh. So I'm presuming that whole data set, the whole column has null values. So like that it goes on. And for this also I got the percentage the same way. And for this we have 26% of the data are missing. And the next step, once we figure out how many data is missing and overcome this issue, the next step or the next question you should be answering is figuring out why data is missing. So it can be a frustrating part of data science, right? For dealing with missing values, you need to use a lot of your intuition and find out and really understand the data in order to perfectly categorize why the data is missing and provide a better solution and better process of overcoming this. So the main question is this: put forth in front of you. Is this value missing because it wasn't recorded or because it doesn't exist? So in the NFL data set, there's a column called time seconds. If you can clearly see it here, time seconds has a little bit of missing values, 224. So for this particular column, the time seconds is like the number of seconds left before the game is ending. So why do we have the missing values for that particular column is probably they didn't record the number of seconds left in the game. So for these type of values, we can overcome it by filling these values instead of dropping. That's what I have explained it here. So you don't want to keep it as end. You want to like fill it with 0 or some other values. And another thing, another column that we have here is penalizing, which also has a lot of missing values. So in this case, if the field is missing because if there was no penalty, then it doesn't make sense to say which team was penalized. So it's safe to say that what I'm trying to say is that that data set has a lot of missing values because it doesn't exist. So it's safe to drop them or do something with them. So that's what we're going to see in this next phase. Drop the missing values. So if you're in a hurry or you don't know why the data is missing or you have difficulty figuring out one option is just to remove those records from the data set. So that's why I did it. Pandas as function drop in it. And access is the one drop the null values which contains in each column. So that's what I did. After I dropped it, I projected some data, the first 5 values. Dot head gives us the first 5 values, and these are the 5 values. So you can see like there are no none samples. This none is just a string. So this is considered as a string. We can later on remove the entire column itself. So right now, as a none value, we have removed it completely from this data set. So let's take a look at the shape. Check the shape of the data before dropping the values and after dropping the values. So before dropping it, we had like 102 columns, and after dropping it, we have like 41 columns. We have reduced a lot of columns, and we have at the same time simultaneously we have lost a lot of information also. So this is the drawback and advantage in using in doing this particular pre-processing technique, that is dropping the null values completely. So the next step is filling in the missing values automatically. So another option is to fill the missing values with null pointer. Null pointer meaning 0, or you could fill it with any other value which is like irrelevant to the data, like -1. So filling with this with numerical data, like everyone does like 0 or -1. So these two values will be ranging between them. And for this, instead of getting the whole data set, I have used all the rows from particular columns, right? From EPA to season. So these are the particular columns. It's like a subset from the NFL data to show you. So I took those data and I stored it in this variable called subset NFL data, and here is your data. So which has EPA, AR, EPA, and so that's not the issue here. The main point you can really focus on is that it has null values here. You can see like there are a lot of null values. So Pandas offers a fill NA function, so we can use that function to fill the null values with 0. So this parameter is specified because in that parameter, whatever numerical value we can give will be represented in place of null values. So that's what has happened here. So let me show you. Instead of FIIP, for this first record, you can clearly see it as null value. And what it has done is, after we are like fill the place with 0, it is 0 here. This is one step of doing it. And another thing is filling NA in with mean value. So before going to that, I'll tell you when to use this fill this NA with 0 values. So mostly try to avoid using this method because it leads to a lot of model building errors. But why do they have this fill NA and use it 0 to replace the null values? Because sometimes in order to overlook this data and to perform exploratory data analysis, we'll replace this with zero values for the time being, and after doing all this exploratory data analysis, later we come back and fill these values with other methods. So that's the main reason, and that's the reason behind doing this filling the null values with 0. So the next idea is to fill these NA values with mean. Rather than filling it with 0, we'll fill the null values with the mean of the entire column. So that's what I've done here. I've used the same subset data, and I've used for loop. So for each column, it's going to fill this mean value of that particular column and place it. So this in place is equal to true means this command is more like DDL in SQL. So whatever operation you perform, it transcends into the original data set also. If you like specify in place is equal to false, it is not going to affect the original data. It's going to generate a view. That's it. So in place is equal to, I've specified it here, so it transfers it to the real data. So now you can clearly see that the missing values, all the missing values have been filled with their respective particular column mean. For example, so we had previously 0 here for the AR EPA, and right now we have 1.125, which is the mean for this particular data set. So this is like using mean and filling the NA values with the particular column's mean. And another method is to fill the NIN with median. Previously fill the null values with mean, but right now we are filling it with median. Exact same process, but instead of mean, we'll be using median. So difference between these two, when should we use mean and when should we use median? So median is robust towards outliers. So if your data has a lot of outliers, meaning you have a lot of data centered away from the mean, it's safe to use median because it doesn't over pressurize the outliers and it doesn't act as robust as mean towards just outliers. So it's safe to use median when your data has a lot of outliers. And when should you use mean? If you feel like your data has not a lot of outliers in it, and more of the values are concentrated towards the center of the curve or towards the mean, you can use this mean function or this particular syntax to fill this null values with mean. So that's the main difference between these two, and that's it for data cleaning. And if you have any doubts regarding this first phase, because there are 4 phases, so after every phase I'll be asking some if you're having doubts or not. So is it clear? Can I move on, or anyone has doubts regarding this? Hello? Hello, am I audible?
Yes, Sashank.
Yeah, Sashank. There is a question in the chat box.
Oh, okay. Oh, sorry, I didn't see it. Oh, there are a lot of
Kindly
questions.
explain difference between mean and median by way of example.
Okay, just a second. So you want me to explain mean? What is the difference between mean and median? So median is basically the center value of all the columns, of all the data we have in a column. So it's just the center value of all of it, and mean is just summing up the entire values of the row and dividing by the whole records. That gives you the mean. So that's the difference between mean and median. So median is less aggressive towards outliers, where mean tends to be more aggressive with the outliers. Meaning mean doesn't generalize better related to the data, whereas median does. So there's a lot of difference between these two, and you should know when to use mean and median. So I already specified when to use mean and median in circumstances. Any other questions? Let me see in the chat box. Is data cleaning is one of the step in EDP? Yeah, it's one of the steps. There are a lot of steps. Explained 4 different steps. So data cleaning is one of the steps. Any other questions? Is it clear? Okay, thank you so much. Can I proceed? Any of you have any other doubts?
So excuse me, sir. Good afternoon, sir.
Yeah, good afternoon.
Sir, yes, sir. A simple question, sir. Please clarify. Is there any? It's enough to import any header file, no, sir, to clean to make the data processing, or any other specific tool is there? In
Tool,
Python, naturally we use a header file.
Yeah,
Okay.
right.
Is there any other specific tool to give the data pre-processing or cleaning or cleansing?
No, if you like take native Python without importing any libraries or packages, you can always use for loop. That's what I've used
Okay,
here.
Okay, sir.
So there aren't any specific packages in Python for you to do this. That's why Pandas gives you the option, drop any, fill any, these all functions. But if you don't want to import libraries and perform these operations, you can always do it using for loop. So let me show you. I've did here. Yeah, see, I've used for loop here. So you can use the exact same syntax because mean is a function from Python. Python it also has mean function. I didn't use libraries for this, for the mean only. But this I used obviously I used a library. You can do the same using Python also with using for loops.
Thank you
Was
so
it
much,
clear?
sir. Thank you so much. Yeah,
Thank
clear.
you,
Thank you, sir. Thank you.
So can I move on? Any other questions? Clear, everyone?
Yes, Shashank, you can proceed.
Okay, I'll proceed. So we looked at the first step. First phase is over, data cleaning. The next step is feature engineering. So the main objective of feature engineering is to create new features from the existing features we already have. So this process is done by hand using Pandas operations that I'm going to show you, like group by, aggregate, or merge. But this is like a lot of work and can be very tedious. And there's a lot of human constraints and imagination. We simply cannot conceive of every possible feature that will be useful for the model to be better. So if you have like 5 or 6 columns, you can try and like get information from them and generate features for each and every column. But for columns such as for data sets which have like 100 or 1000 columns, it's simply not feasible to go about every feature and try to understand each and every feature and try to generate engineer features for each and every column we have. So that's why the importance of creating proper features cannot be overstated, because machine learning model can only learn from the data we give to it. So machine learning models performance is only from the data that we provide it to. So these are the 5 steps or crux in feature engineering. Determine which features are the most important with mutual information. Invent new features in several real-world problem domains. Encode high cardinality categoricals with target encoding. This is nothing but label encoding you might have come across, because if a data set has a location, for example, we'll take Chennai, Delhi, Mumbai, machine learning model cannot understand text or strings. So that's why we label encode it to them into a numerical value, like Chennai can be 1, Delhi can be 2, and Mumbai can be 3. And using this method, we have feature engineered and provided a solution for the model to understand what cities that we are trying to represent. And the next step is create segmentation features with k-means clustering. That's the final step. And decompose the data's variation into features with PCA. So PCA will later look on. That's like completely different category, which comes under data reduction. So right now we'll stick on to feature engineering. So the goal of feature engineering is simply to make your data better suited to the problem which you have at hand. I'll give you a real life example. Like when you see weather, like Google Weather or some sort of AccuWeather or any software, you have a lot of indexes like humidity index, we have temperature, we have wind direction, wind speed, and all these concepts. But an apparent temperature is also known as how it feels outside. Like you have come across, like it could be 25 degrees, but it feels 28 degrees. So what it feels like is like a real world example of feature engineering. You might perform feature engineering to improve a model's predictive performance. So these 3 are like the goal and endpoint of feature engineering. Reduce computational or data needs. So computation meaning when you like feature engineer and create new features from the existing features, you might want to drop the existing features you already have and use the newly engineered feature to give it to the model and build it. Improve interpretability of the results. I'll come to that. We'll see the implementation of that in a few seconds. And this is another example I want you to understand. So exactly what is feature engineering and how we can proceed and go about the idea and implement those. For example, this is a base model. and this is the x-axis as the length and y-axis is the price. So what I'm trying to say is that the key idea here is that the transformation you apply to a feature becomes in essence a part of the model itself. So if you have a square foot, if you're trying to predict the price of a land and you only have the length of each particular square feet, like let's say 1 square foot is like 30 centimeters, right? So we have like 30 centimeters, only 30, 30, 30. And we use only those particular information. So 2 square feet meaning 60 centimeters approx, like that. So 60, 30, 90. Only using that, we do a scatter plot, and you see this is the base model we get from the original data we have. So we try to fit a line in between this. You can clearly see this is a parabola, almost a curve, which is going to be a parabola eventually. So this is the original data set. But in order to really understand the price, you always compute it in area. So we can achieve that by squaring the length. So when you square the length, we obviously get the area. And now we'll use the area feature and the price feature and correlate them and see how it goes. So this is the extended module. So we have like on the left, we have price and area, which this is after the machine learning. This is the prediction after you fed in the area data, and the machine learning model predicted to be this, and it fit the line perfectly. This is a linear regression problem. So it fit the line perfectly when you have provided area function. And after also providing the area, when you like also use the length feature, it fits the data perfectly. It fits a beautiful parabola line per length also. Before feature engineering, this is what a model predicted it to be. You can see a lot of inconsistencies, and this is not quite a good model because there will be a lot of errors between data points. So after you've engineered a new feature called area, and you use these two features, length and area, to train the model, and after training, when you use that trained model and predict it on the same data set, this is what we get. So this should like paint a really good idea on what feature engineering really is. So let's look at an example. For this example, I've used concrete formulations data set, which contains a variety of concrete formulations and the resulting product's comprehensive strength. So comprehensive strength meaning the ability or the amount of strength or concrete has, or amount of strength it can withstand. So that's what a target variable is going to be. So I imported it, and I've printed out the first 5 records for it. So you can clearly see there are a lot of columns for it. Cement, blast furnace, fly ash, water is amount of water you're getting in the mixture of the cement, super plasticizer, coarse aggregate. Coarse aggregate is nothing but the stones that we use to grind, and fine aggregate is after grinding what is the value we get. So these values are nothing but the weightage, the weight in units. So this is nothing fancy. This is just a weight. There's no unit specified here, but it is weight in kg. So comprehensive strength has a unit on its own. So that's what we're going to figure it out. So as I said, there are a lot of various ingredients going into each variety of concrete. So let's feature engineer some of these new features with some of the existing columns that we have. So first I took a look at the columns, and what I'm doing next is that I am building a machine learning model, practically building a machine learning model before feature engineering, and get the results, and do another machine learning model with feature engineered results. So I'm going to show you the result before feature engineering and result after feature engineering. What results do we get? So for this, I've used random forest regressor and score. Random forest regressor is nothing but taking votes from a lot of decision trees. I'm thinking you all know. And second is cross validation score. Cross validation score is nothing but it divides the whole data into five chunks and trains on each 5 chunks and gets the vote from all of those remaining 4 chunks. So that's what is going on here. So I imported random forest regressor from sklearn, and the criterion is MAE. MAE is nothing but mean absolute error. So that's what we're going to be evaluating this model on. Random state is equal to 0 is nothing but the seed that we're going to be setting. So I've set it to 0, and I've used cross-val score, as I said already, and use this regressor here, parameter. X and Y are training features and a target feature. CV is equal to 5, meaning split the data into 5, and scoring is negative mean absolute error. So when we get the final score, I'm multiplying it by -1, so it just returns MAE. Nothing. There's no difference between negative mean absolute error and MAE. So just for some research purposes, I did this. Nothing fancy here. And after training and after getting the score from cross validation, we got like 8.947. Mean absolute error is 8.947, meaning the predicted data is like 8.9 values away from the original value. So you can like paint a picture. So it's like 8.9 away from the original value. And now what I'm going to do next is this value is like before feature engineering, and the next is we'll engineer some of the features and after understanding the data. So after I looked at the data, I came to know that there's always a ratio between fine aggregate and coarse aggregate. So that's what I did here. I engineered a new column, FC ratio, FC nothing but fine and coarse ratio, which can be obtained by dividing the whole fine aggregate by coarse aggregate, and I got the ratio for that. And this is the next feature I'm going to engineer is aggregate cement ratio, which is nothing but the coarse and fine aggregate both go into the making of cement. So these both features or these both values make a cement. The end product will be cement. So what I'm going to do is that I'm going to add fine and coarse aggregate and divide the whole value by cement. So we got the aggregate for cement ratio. And water, we all know that they always add water to the cement, so we'll also get that ratio and let's see if the model's performance is improving. So we have basically given extra information for the model to build wisely and get better predictions. I've used the same metrics, random forest regressor, same evaluation metric, mean absolute error, and same cross validation CV split or CV split 5, and negative mean absolute error, which naturally returns MAE. And you can clearly see here that MAE score after feature engineering gives us about 7.4 to 7. So we have like reduced the model's error by 13% just by feature engineering 3 of those features. So I think this could be this could paint a better picture for you that how feature engineering can help the model understand with the existing data that we have. So that's it for feature engineering. So I'll check my comments. If any of you have any doubts, you can ask right now. Any questions? Is it clear, feature engineering, what it really does? Hello?
One question from Mr. Bharanidharan. Please explain feature extraction.
Feature extraction, just a second. So feature extraction is nothing but feature engineering. So it's a sort of feature engineering, but extraction meaning you leave a lot of features alone and extract only the features that you need. So that's for like a completely different topic. It doesn't come under feature engineering, but it's true to each data set. Like I can't really show you how you can extract features like it from the existing features, because for different data sets we have like different feature extraction methods, which I'll be showing you later in this course. So that's going to come under data reduction. So don't worry, I'll be explaining what exactly feature extraction is, but it really doesn't come under feature engineering. It's just extraction. Is it clear? So could you please share the data set and notebook file in chat box, sir? Okay, after explaining, I'll share it to you. It's in my GitHub. Yeah, okay, thank you so much. And for this question, can you please share the data set and notebook file in the chat box? Yeah, it's in my GitHub. After explaining, I'll surely share my GitHub link. I'll put the GitHub link in this chat box. You can go and check out that. It's free. Okay, any other questions? Can I continue? Okay. So after these two methods, we have data transformation. So this is the important part of like data pre-processing, where majority of our focus really depends on this data transformation. So data transformation has a lot of steps that we can do, like normalizing, smoothing, aggregation, and generalization of the data. Normalization is just like standardizing the data. I'll explain to you what it really does. And next question: why scale, standardize, or normalize the data? So scale is different, and standardize or normalize both mean the same thing. And what is the difference between them? And why do we do them? So why do we scale or standardize or normalize the data? So many ML algorithms, such as neural networks, regression-based algorithms, like you have nearest support vector machines, and linear regression, and all this, and support vector machines with particular radial bias kernel functions have a lot of for it to perform better, it needs to like go about from one feature to another feature, and it really increases the complexity of the model. So that's why we perform these steps in order to converge, in order for the model to converge better and get to the global optimum, to get the minimum error. So that's why we do it. I'll explain it more clearly. So what is the difference? One of the reasons, it can be easy to confuse yourselves with what is scaling, what is normalization, because basically they all try to understand, their goal is the same and they all mean the same thing, but there's some differences in between them, and the terms are used interchangeably, and it can be more confusing. So I'll be explaining it what it really is. The difference is that in scaling, you will be changing the range of your data between the range given by you. So normally it's between 0 to 1. So if your data set has a range between like 100 to 10,000, you can scale those data between 0 to 1 with the help of scaling. So that's what scaling does. So that's what I've specified here, like a scale 0 to 100 or 0 to 1. You want to scale the data when you're using methods based on measures of how far apart data points are like. So in real world example, I'll give you one thing. You have like yen, which is a Japanese currency, and US dollars, you all know it is a US currency. When you apply this data set to a SVM or KNN algorithm, a difference in $1 can be a difference in $1 is huge than the difference in yen between 100 yens. So what I'm trying to say is here, $1 costs about 110 yen. So if you use the same exact scale for your machine learning model, it will classify that difference between 1 and 2 yen is as big as the difference between $1 and $2. So obviously the difference between $1 and $2 is going to be 110, but between 1 yen and another yen, it's going to be 0.0111. But when you supply this type of data to your model, your SVM model is going to think that a difference in 1 yen is as large as US dollar. So it's going to specify that 0.0 value, take that weightage and compare it to US dollar, which is going to be 110. So that's why in these type of examples, we use scaling. Scaling, what it does is that it scales your entire data set between 0 to 1, keeping the ratio between the data points exactly the same as it was before. So that's what it's doing here. So this is a formula. So Z is nothing but the scaled value. So for each X, we're going to subtract it by the minimum value of X for that data set divided by the range between those two values, the maximum value and minimum value of particular column. So that's the formula that we're going to be using here, and that's the universal formula everyone uses for scaling values. And I've used NumPy's random exponential function, which is going to create an exponential graph of size 1000. So this is just a random plotting, just the plotting of the exponential graph that we're going to have, and it returns the random values of those exponential values. Now this is just a scatter plot. Now let's see the histogram plot for the same exact data, original data here. The name is original data. And for scaling purposes, we'll be using min-max scaler provided by MLExtend. This is another library. There is also a min-max scaler in sklearn, but just for varsity and diversity purposes, I've used MLExtend to just show you there are a lot of different libraries that we can also use for different features and different functions, which also provide the same thing, nothing different in importing different libraries. So what I've done is I imported this min-max scaling function, and you fit this original data into that scaling function, And the column I specified is 0. We already have just one column, so that's going to be like it's going to scale the values between this one column, and I've stored all those scaled values in this scale data variable. So let's plot and see how it looks like. So I've used matplotlib for this, and I've used cbound for displot meaning histogram plot with a line on it to but it leads to better visualization. Just a histogram plot but with a line on it. No difference between histogram and displot. So this is our original data. This is what our histogram data for that exponential graph looks like, and you can see the range which is between 0 to 8ish, almost 8, and after scaling, it has reduced. It has like compressed all those values between 0 to 1, maintaining the same distribution. You can clearly see what's happening. They both have the same distribution, they both have the same ratio, but the scale is different. Which original data has 0 to 8, but scale data has 0 to 1. So when we scale these data, our model better converges, because for problems which use a stochastic gradient descent or gradient descent, for it to converge to global minimum, it needs to go do it quickly and precisely. So for that, we use scaling. So if it's between 0 to 1, it does it quickly. So basically, when you scale the data, the model will train faster and converge better and find the global optimum more efficiently. So that's the main purpose of scaling. And second is normalizing, or normalization in this circumstances, normalization or standardization, whatever you want to call it. Normalization is a more radical transformation. So the point of normalization is to change your observations so that they can be described as a normal distribution. You all know what a normal distribution is. Normal distribution is nothing but a Gaussian distribution, also known as a bell curve. So this is a specific statistical distribution where a lot of those values concentrate among the mean, and there will be a few outliers in both the positive and negative values. So equal observations fall between the mean and median, which is going to be the same for normal distributions. The mean and the median will be same. And why do we normalize? So we normalize because when our data's distribution is like positively or negatively skewed, which I'll explain it to you in this upcoming phase. Positively and negative skewed, your model will become a lot biased towards one particular phase. So in order to avoid doing this, we'll normalize the data and get center or some of those values and majority of the values between the mean, and naturally you're going to have a less number of outliers, which is going to affect the model. So that's why we normalize, and the method or the formula that is used for normalization is this. So z is equal to x minus nu by sigma, which is nothing but nu is the mean for that particular column, and sigma is nothing but the standard deviation. So standard deviation, for that standard deviation you want it to be 1, and mean, it could be anything for that particular column. So what it's going to do is that get the mean value to 0, and the mean and median is going to be same for the normalization. So for this step, we're going to use boxcox. Boxcox is another library which is imported from SciPy. SciPy library, many of you will be familiar. So from that, I've extracted boxcox and applied the original data we already have. So this is the original data. I've applied to this boxcox function, which is going to normalize the data, and I visualized the data. So this is this plot, as always, used in previous visualizations also. Visualize original data and normalized data. So there's a significant amount of difference that you can draw from these two graphs. One, the left histogram is the original data, which is not scaled, which is 0 to 6, and right is the normalized data. You can clearly see the transformation between this and this. So this original data is positively skewed. Positively skewed means there's a lot of values which is positively sided from the mean. And this normalization, when you apply normalization to this data, it is like distributed the data evenly, and we have a few or less outliers. But when you normalize the data, it's going to maintain the range the same. So from here we can see that it's 0 to 6. Here it's -4 to 2. So that's going to mean the same thing. The range is same, but the distribution has been changed. So that's the main difference between normalization and scaling. And there are a lot of methods for scaling. we can use min-max scalar, robust scalar, standard scalar, and normalizer sparingly. So normalizing sparingly doesn't mean anything fancy. It's just L2 normalization or L2 regularization, which I'll be explaining in the next phase. So let's see what each of these scalar does, because min-max scalar, robust scalar, standard scalars are one of the most important three scalars which is provided by sklearn. And let's see under which circumstances we can use each of the scalar for a better model building. Original distributions for our base plotting, for our base data, I've created 4 different distributions. One is beta distribution, one is exponential, normal platykurtic, and normal leptokurtic. And I've also included bimodal. Bimodal is nothing but there will be 2 peaks for that particular function. You all know exponential curve, beta curve is also almost similar. Platykurtic and leptokurtic, I'll be willing to explain to you. So platykurtic meaning your kurtosis at the peak will be less and your outliers will also be less, but the peak will be a lot higher. So that's the that's like the difference between platykurtic is that there will be a lot of peak and the kurtosis will be less at the peak. And leptokurtic is that you have a lot of data centered towards the mean. So nothing complex. It's just a random plotting. This is not the focus here. So I'm plotting all those distributions using Seaborn. Seaborn is another library for visualization. And instead of plotting the histogram, I plotted the kernel density function. The kernel density function is nothing but the probability density function. So it is going to plot the probability density function, and it like specifies the density for each of those distributions. So x value obviously contains the range, and y value is the density. So density meaning the importance of each of these values. That Okay, sorry for disconnecting. My power went out. I had to reconnect this meeting using my mobile data. Sorry for the inconvenience. Am I audible? Am I clear right now?
Yes, Sashank.
Yeah,
Yes, sir, you are audible.
Okay. Thank you so much. Just a second. Is my screen visible right now?
Yes, sir, screen is visible.
Yeah, okay, thank you so much. So this is the KDE plot or the original distributions. I've created the base layer and the base model, base representation, and we'll be working on this. We'll be using min-max scalar and all the scalars on this particular data set as our base model. So this is just the samples or the first 5 values of the data set we have: beta, exponential, normal platykurtic, normal leptokurtic, and bimodal. So right off the bat, we'll see what the mean values are for each of this data. So because we'll be comparing these values after we scaled also. So that's the purpose of visualizing or like representing these mean values beforehand. So we have like 49 for beta, 10 for exponential, 9 for normal p, 10, and negative value for bimodal. So this is just the normal scatter plot I did for your reference purposes. Nothing going on here. No conclusions you can draw from here, just for visual representation. And I've also added another feature, which is a normal big, which means like a normal distribution, which is going to be very big, and its value consists of a lot. You can see the scale here. It's almost 10. It's almost 10 million towards this 10,000. So I've like plotted it using KDE, and this is a normal distribution you can see, which is really big. And the mean for this distribution is going to be 999,629, which is almost nearly a lakh. So let's apply min-max scaler to this particular function. So I have imported preprocessing.min-max scaler, which is from sklearn, and used that scaler and created a scaler and I fit that scaler for that particular original distribution. I've already represented it to you. And what I'm going to do next is that visualize. So after scaling, let's plot all of those different columns we have, all of those different plots we have, like beta exponential. So let's see how, after scaling, what it really does. So after scaling, we can really see that from like -40 to 80, the scale, we have like reduced it to -0.2 to 1.2. So we scale those values, maintaining the integrity of the original data. So all those ratios and all those distributions remain the same. Just we have scaled the values to be between -0.2 to between 1.2. So this is the shape of each distribution, and which remains the same, and the values are between -0 to 1. So let's see the minimum values for beta example, which is 0 to 1. You can the minimum value is 0 and the maximum value is 1. And let's look at the minimum and maximum values for each column prior to scaling. So before scaling, let's look at the minimum and maximum values. So these were the minimum and maximum values. So we have scaled from these whopping large values to we constrained this whopping large values to be between 0 to 1. So we have all the minimum values for all of those columns, 0, 0, 0, and maximum is 1, close to 1, 1, close to 1, and all. So this is what min-max scaler really does. And next we have robust scaler. So robust scaler is like it subtracts the column median and divides it by the interquartile range. Interquartile range is nothing but the 25% of data between the 25% and 75% of the data. So it divides the column median by the interquartile range. So why do we use robust scaler? So robust scaler is used for when you have like a lot of outliers and you don't want to miss those values. You can use robust scaler. It generalizes the data for outliers. So when you have like anomalies and you want to keep them, and you think that those anomalies really bring something to the table and it really helps the model to understand, and you want to scale the values, you can go ahead and use robust scaler. So that's the purpose of using robust scaler. I did the very same. Robust scaler is available in sklearn. I've imported it, fit the scaler for that particular model, our original model, and I've plotted the kernel density plot for that robust scaler, and we can clearly see that for each of those representations we have like different distributions, but maintaining the same structure, almost the same structure. So this is what happens, but the scale is the same, -4 to 6. Previously it was like between 2 to 8ish, but now it's -4 to 6. The scale remains the same, but we have scaled those values to be between the median divided by the interquartile range, which is going to be better for the outlying values. So let's check the minimum and maximum for each column after robust scale, after using robust scale. So prior to scaling, we have like we had like 16, 0, 3, -22, 27, and all those stuff for minimum and maximum values we have. But after robust scaling, we have these values. So we have reduced by 100%. These values we have reduced by 100%, like -3, 0, 2. So it all lies between this -3 and 2. So that's a win here. And the range of the values for each feature is much smaller than for the original features. So the ratio remains the same, but we have scaled according to the outliers. The next, standard scaler. Standard scaler scales each column to have 0 mean and 0 unit variance. So meaning standard scaler can be applied when your data doesn't have any outliers, and you think you want to like fit the model perfectly scaled and get the same amount of structure and integrity of the model. So basically, robust scaler and standard scaler does the same exact job, but you use robust scaler when you have outliers. when you don't have outliers and you think I don't care about the outliers, I don't want outliers, I just need the data to be scaled, you can go ahead and use standard scaler. So that's what it really does. I've did the exact same thing. I've plotted the kernel density for each of those particular functions of each of those mathematical functions, beta exponential, and this is what we get. So this is exactly the same structure, but scale. That's it. The scale of this value has been reduced. They can clearly see between these columns. So next step, we'll check the minimum and maximum for each column after standardly scaling. So these are the values. So it also lies between -3 and 2 for some of those columns and goes up to 6, which is perfectly all right, because previously we had values between -40 to 80, and right now we have between 2 to 3 or such. So that's the difference. And next step is normalizer. So normalizer is nothing but an L2 normalization by default. So it applies L2 normalization, and after applying L2 normalization, we get this plot. So for all those, remember we used normal big. So what it did was it normalized each and every value to be 0.999. So 0.999 to be. So that's what normalizer does, but we don't use L2 normalization for data for cleaning or like pre-processing data that much. So this is just for reference purposes. Me myself, I have never used this function for normalizing my data. So it's also another form of normalizing data, but refrain from using these methods. Avoid this method. It really basically does the same exact job as like what robust scaler and standard scaler does, but it does in a different way, which applies L2 normalization. So I wouldn't really recommend using this method, but just for research purposes, I've showed you. And next, you might have forgot what each plot looks like after scaling. So what I did was I've combined all those plots into one single plot. So min-max scale, the original plot after scaling, after robust scaling, and after standard scaling. And I haven't included normalizing because, as I said, refrain from using that method. So that's not as important as it sounds. So these are the four plots. So leftmost we have the original distributions, and we have the scale. We have the plots for min-max scaler, robust scaler, standard scaler. So these are the representations. So most of the distributions are on the similar scale, and you can clearly see that min-max scaler doesn't distort the original distributions, but has the same values. So this is like sticking on like this because since we have scaled this, these are so small, you can really see these values, but this plot over on the left is very big. It can't really represent in this visualization pattern. So that's what's happening. These three plots are so small since we scaled them. So basically this represents this plot. That's it. Let me show you the original plot we just did. So this is just that, but hence the scale is so small, we can only see just one line, which is the normal leptokurtic plot. So that's what's happening. And as I said, when to use each of those? Use min-max scaler as a default if you're transforming a feature. It's non-distorting. So my recommendation is that always use min-max scaler according to your data. So your first preference should be scale the data. So min-max scaler comes in quite handy. So you can always use min-max scaler. And robust scaler, standard scaler, as I already said, there's a difference between those two. When you have outliers and you think those outliers have affect the output variable of your model, you can go ahead and use robust scaler. And if you don't, you can use standard scaler. Completely fine. And this is just another small difference plot, difference representation I found on Google. So that's why I imported and pasted it here. I will like paste this link in the chat box. Paste this link for this notebook in my chat box, and it is in my GitHub. You can go ahead and later look onto that notebook for your references. And the last thing, or the last phase, data reduction. So when you collect data from different data warehouses, okay, before going to the next phase, you have any doubts? Completely forgot, sorry. Let me check for this particular thing. Any doubts before going on to the next phase? Sorry, I forgot. scaling, normalizing, standardizing. Any confusions, any doubts you have? Any clarifications I should make?
Yeah,
Sir,
one
is
query, sir.
scaling and normalization difference?
Sorry, I can't hear you.
Difference between scaling and normalization.
Okay, difference between scaling and normalization. So scaling is that you compress those values between a certain range. So as I specified you, our original data had like -40 to 80. Our scale, the scale of the data was -40 to 80. But when we scale those data, we can like compress those values between the range 0 to 1 while maintaining the ratio between those values. So that's scaling. Normalizing has nothing to do with scaling, like scaling the range of the values, but it really changes the shape of the distribution of the original model to a normalized curve, or else bell curve or Gaussian distribution. So Gaussian distribution has a mean of 0 and a standard deviation 1. So that's the difference.
Okay, thanks a lot, sir.
Thank you. So can I move on to the next phase? Any doubts? Let me check my Google Meet chat box real quick. Okay, do we have to scale data always even if all the features are equally seen? No. Using min-max scaler is not always the right option. If you think your data has like equal intervals between them, so for example, you are predicting your house prices, and house prices ranges between like for 2 square feet it can have some values, and for 50 square feet the price is going to be different. So there's going to be a lot of difference between those data points. So under those circumstances you can go ahead and use min-max scaler. But other than that, when you have like your independent variables and dependent variables, or what I'm trying to say is that correlation between the dependent and independent variables is less, and the changes produced by those dependent variables is less compared to that, you can refrain from using min-max scaling. It's not needed. So was I clear?
Sir,
Should I explain it even more?
sir, one query.
Yeah.
One small query. In that data set, suppose all the features are between, say, 1 to 10, all the features. So is it necessary to scale in that? Is it necessary to scale in that case?
No. It all comes down to you. 1 to 10, if you want, you can scale it, but scaling doesn't bring the difference when the values are between 1 to 10. So there's not really much going on. Even if you scale, you're going to get the same results. So because it's between 1 to 10, it's very low range for a data set. Our machine learning models are obviously going to perform better even if you scale after those also. Even if you keep the data set between 1 to 10, it's going to produce the same results. Scaling is the only option when you have the scales or the values between the scale is so large. Like in this case, -40 to 80 is quite large. And another important thing to understand here is, another thing I would like to mention here is that when you have features like let's say house prices, for example, you have square feet, like 1 square feet like goes around for the price of 5,000 rupees, and like 10 square feet the same 30,000 rupees. So under these circumstances you got to scale those values according to those data. So you need to scale not for one particular column but for the whole data set. You need to scale right from the lowest value for the square feet till the maximum value for the prices. So under these circumstances you should not scale according to your one particular column. You should scale for the whole data, because we have values ranging between 100 even going till crores also. So plotting those points in graphical representation is impossible even for humans. So imagine for machines, it's really it will be really tough, and it will take a lot of time for the model to converge on the global medium. That's why we scale or normalize. So is it clear?
Yes, sir.
Okay, any other doubt? Thanks for clarifying. Okay, thank you, sir. Glad I clarified it. Okay, there are not any other questions. I'll move on to the next phase, which is dimensionality reduction. So this is like advanced stuff, advanced pre-processing stuff. So dimensionality reduction is a process of reducing the dimension of the feature set while maintaining structure and usefulness. When your data set has a lot of features, like say 2,000 columns, 10,000 columns, it is really not feasible for you to fit in the entire data set into the model and shove it down its throat and asking it to like give me predictions. So your model is going to fail, and it will be far more complex for you also to understand it. So that's why we use dimensionality reduction. So the reasons for dimensionality reduction is that very large number of features for each training instance may take training extremely slow. So when you have a large amount of data, obviously your training is going to get really slow. And it is the next main important thing is that it will be difficult to visualize the data. For 102 columns, it's actually fine. It is quite large, but it is actually fine. We can visualize those. But for 10,000 columns, it's just not possible to visualize all those columns. So that's why we use dimensionality reduction. So the pros is that for using dimensionality reduction, after using dimensionality reduction, the pros are you get less time in training, and the visualization is going to be easy. And sometimes it also results in higher performance. I've included may not because sometimes your data columns are going to be less. But if you have a large number of columns, your result is going to get better. And we have only one important disadvantage here. You will lose a lot of information here when you apply dimensionality reduction. But that's up to you. That's on the loss of the domain expertise hand. If you okay of losing information and you think that those information are quite useless, you can go ahead and reduce the dimensionality using the following methods that I'm going to specify in the next phase. Or else you can use other pre-processing methods. And now dimensionality reduction can be achieved in the following ways. So as I said, faculty asked what is feature extraction. So I'm going to be explaining right now. So before that, feature elimination and feature selection. So these are the three main things. And feature elimination and selection, you usually don't have a blueprint to follow for doing these type of stuffs, because elimination and selection should be you should do those stuffs from understanding the data. So each data can be different, and elimination and selection processes will also be different for one particular data set. So these two topics are true for their own particular data set. So this should be done with your intuition and your vision, and what you think is right and what feature do you think will not be helping, you can eliminate those things. And selection, so basically understands and you can express this the same thing, feature elimination, selection. So feature extraction, the main thing, we create new independent features where each new independent feature is a combination of each of the old independent features. So we can use these techniques. There are a lot of techniques like PCA. For linear problems, we have PCA, principal component analysis, and SVD, single value decomposition. But in this session, we'll look at PCA. And for non-linear problems, we have TSNE, nothing but T distributed stochastic neighbor embedding. So TSNE is highly advanced concept. I've also explained it here, try to understand it. But let me explain PCA first. So there are a lot of main approaches for dimensionality reduction. The main are these two things, projection and manifold learning. So projecting high dimensional data and low dimensional hyperplane to minimize the variance, which we're going to be using PCA for this. And manifold learning. So manifold learning is nothing but it is the best approach. It is used for non-linear problems and is the best approach for dimensionality reduction, involving the patterns which cannot be nearly fit by linear problems. So that's why we use manifold learning, which uses TSNE in this case. So what it really does is that it takes the weighted average between those neighboring points and sums it up and get those values. So that's what manifold learning does. I'll explain it to you briefly. So projection, PCA, principal component analysis. It is the main method used for linear dimension reduction, as I specified. It also performs linear mapping of the data to a lower dimensional space. So in other words, it fits a hyperplane or fits a line and selects that line, which reduces the error between the points, which minimizes the variance between those points, and selects the hyperplane and projects it on the hyperplane and just transforms the dimensions into whatever the dimension you specify. So all the components are linearly uncorrelated, and each of these new features or components created after PCA are all independent of one another. So this is just a normal visualization for your purposes. So this is the original data. We have two components, obviously feature 1 and feature 2. So what we try to do is that this this is just a scatter plot. You can clearly see this is the original data. We have two features. We have plotted two features. You want to reduce this data to one dimension. So there are two dimensions for this. You want to reduce it into one dimension. So what we're going to do is that can you see my cursor? Can you see my cursor? Okay, I'll assume you can see. Okay. So what PCA really does is that it creates a hyperplane 1 and 2. So we have specified 1. So it's going to create a hyperplane between these data points, which really minimizes the error between them, and it projects those points onto the plane. So these all points will get projected onto one plane, and it really transforms the 2 dimension into 1 dimension. So like this. So this is for this. You can see that diagonally represents the one. So we have reduced one feature. We have reduced from 2 dimension to 1 dimension. And after this, another thing I would like to specify is that principal component analysis is used for unsupervised learning. So use these concepts when you have unsupervised data set and you want to reduce the dimension. You can use PCA. For supervised learning, PCA is not that much needed. If you want, you can use, but supervised learning, nobody uses PCA for that. So for unsupervised learning, go ahead and use PCA. So this is what it really does. And for this, for explaining this, I've used Iris dataset provided by sklearn. I have in my PC, so I've imported that CSV. So there are 3 types of Iris species. We have versicolor, setosa, and virginica. So for each of those classifications, we have 4 different features like sepal length, sepal width, petal, and petal length and petal width. So here we have 4 different features that goes into model building. But so meaning 4 different dimensions we have. So we want to reduce these 4 dimensions to 2 dimensions. That's what I'm going to do right now. So our Y variable will be an Iris species. So species nothing but we have 3 classes. And as I've said earlier, I'm going to standardize this data set, and I've used standard scaler because I don't have any outliers. So I'm using standard scaler, and I transform this for Iris data set basically, and imported PCA from sklearn. Sklearn provides PCA, and this parameter is that I've imported it as sklearn PCA, and n components is equal to 2, meaning how many dimensions you want your model to have. So from 4, I want 2, so I should specify 2, and I'm storing that into this variable, and I'm fitting my X-Iris data model into this particular classifier, sklearn PCA. So next, I'm going to plot this after applying PCA to this data set. I'm going to plot it. So that's what I've done here. So zip, usually what it really does is that it zips it combines 2 different lists. So for Iris setosa, it combines Iris setosa in blue and Iris versicolor red. Iris virginica should be green. So what I've done is that given 2 lists and I zipped it. So for each of those classifications, I'm going to classify it as each of those colors I've represented here, corresponding colors to be precise. So I've used scatter plot. So principal component 1 should be my X label, Y label, and legend is nothing but your title of those or your label. What labels are you going to be using? So I'm going to specify it using legend and the location of those label, and I'm plotting it. So after applying principal component analysis to be 2, so from 4 we have reduced it to 2. So you can clearly draw a margin between these. So this blue, you can see this is Iris setosa, right? You can clearly see this is away from these two other classifications. And after doing this, you can go ahead and use K nearest neighbors or K means clustering for classifying these objects. So as I mentioned earlier, this is unsupervised learning. So you cannot use machine learning models. If you want, you can use, but K means clustering and K nearest neighbors provides better results. And for this is just a basic PCA. So for further understanding, I've done another implementation of PCA. For this, I've imported breast cancer data from sklearn, and what I've done was this is just a description of the data. So we have 569 data sets, records, and these are the attributes information: radius, sexual perimeter, area, smoothness, and all of those different. And our Y variable is going to be malignant or benign. So this will be our labels. So this will be our libraries provided from the sklearn dataset. What I'm going to do is take those feature names. Feature name is nothing but the input variables, and I have created a data frame from that. So this is going to be our input variables. So mean, radius, mean, texture. So guessing from the fact that we have a lot of things, I'm going to specify that we have like 30 to 35 different columns. So meaning we have 30 to 35 dimensions for this particular data set. So that's a little bit high for this data set. What I'm going to do is reduce those 30 features to 2. So as we noticed before, it is difficult to visualize high dimension data. So we'll use PCA, and let's see what happens. It's the same methods. I've used standard scaler. Excuse me. I've used standard scaler, and I fit the data set to the scaler, and I've transformed the data. So scikit-learn uses a very similar process to other pre-processing functions, and this is the best PCA that any library in Python can offer. So scikit-learn offers the best PCA functionality. So I'll recommend using PCA from scikit-learn, and I've imported it obviously again. And as you want like to reduce those 30 features to 2 features, I specified it. N components is equal to 2, and I'm fitting those PCA to the scaled data. So keep in mind, I'm fitting those PCA to the scaled data, and I'm transforming it. And after doing those, you can see the shape of the original data, which was like 569 rows and 30 columns, has been reduced to 569 to 2 columns. So we've reduced like 28 columns. We have eliminated 28 columns and reduced it to be 2. And let's plot the graph for this, scatter plot to be precise. And this is the scatter plot. So after this, after plotting this, you can like clearly draw a boundary between those two. We can't really use logistic regression for this because we have a lot of boundaries present in between them. So we can use k nearest or random forest for this particular problem. Random forest, k nearest, anything is fine. K neighbors also is fine for this. So we can, after doing this, we can go ahead and use these machine learning algorithms for this particular data set. So that's what I'm trying to specify here. And then one more thing, this is just for research purposes. I've plotted, I've like outputted the components, PCA components for each particular cell of this data. So this is, you can take this as like support value of each particular data. And as I've already mentioned, each row represents a principal component, and each column relates back to the original features. So what I did next was understand how each of those features are like highly related to the output variables. So how each of these variables are like important to predict the output variable, which is going to be 0 or 1 in this case. So this is just a heat map. I've used Seaborn for this. So heat map represents like the highest color is like deep yellow. So deep yellow represents, it has high correlation between the classified number to that particular dimension we have. So blue being the lowest variance, so we'll like refrain from using those variables. So that's all we have to specify here. So that's it for PCA. Any doubt you have in PCA? Any explanation? Or if you have doubt in what PCA is, I can explain it to you more clearly. Let me check. You have any doubt in PCA, principal component analysis, and its concepts or how it's working? Hello?
Yeah, no doubts.
No doubts. Okay, clear what really
Sashank.
PCA does?
You can carry on.
Okay. Good. So we have looked on upon what projection really is, and the next we'll look what is manifold learning. So manifold learning, TSNE is like highly complex algorithm. It is not even a machine learning technique. It is more like an algorithm we use to do this. So it's called TSNE. It stands for T-distributed stochastic neighbor embedding. So which maps the points in high dimensional space to a low dimension, and the distance between the points remains the same. Like I said, it takes the weighted average from its neighbor and collects them and projects them. So when you should use TSNE when you have a non-linear problem. So for this problem, you had like a linear. You had a linear problem for this and all. So you can like linearly separate these values between them. So like how we applied a line between them and projected those points to convert into a one-dimension data. But for this TSNE, you should use this when you have a non-linear data. So I'm going to explain it right now. TSNE creates a probability distribution using the Gaussian distribution that defines the relationship between the points in high dimension shape. It optimizes the embedding. So clearly, these checks are what I explained just right now. And it uses stochastic, not deterministic. So stochastic being we don't really know what each point represents. That's why we use stochastic neighbors. So, you might have as well as heard stochastic gradient descent. It uses the same concept to this also. And that's what happens. And this algorithm, we can specify it in 2 steps, and which dictates the relationship between various neighboring points and creates a probability distribution and gets a weighted sum. Why do we need TSNE? So, like I specified earlier, PCA can't capture non-linear dependencies, but TSNE can. So let me plot it, show you. I've used sklearn datasets and imported Swiss roll function, and I've plotted that function for your visual representation. It holds like 1,000 samples, which has a noise of 0.2. You can control it however you want. Random state is equal to 42 is nothing but the seed I specified to you already. So when you rerun the whole data set again, it really doesn't change the values. So it's like setting a seed like a pillar, and you like go turn around and go around this pillar same again and again. So that's what random state does, and nothing fancy going on there. So I added a subplot and I plotted the values. So this is a 3D plot. This is a Swiss roll 3D plot. So consider this like a data set. So your data set follows this pattern like a Swiss roll, and you can't project these values, or you can't fit a linear line and use PCA for this, because it is impossible to fit a linear line on this. So that's why under these circumstances, for unsupervised learning, we use TSNE, which is not limited to linear projections. So when we use TSNE from sklearn, TSNE from sklearn is the best. So I recommend you to use TSNE, which has components of 2. Likewise, I specified how much data reduction should happen and how many features you want. So I specified 2. Verbose is nothing but the information, the amount of output information I need. So 2 meaning maximum output information, 1 being minimum output information. Perplexity is 40 and iterations is 300. So amount of iterations we need for it to happen, 300. I have transformed it and I have plotted it. So after applying TSNE for this model, we can clearly draw a boundary between these particular values. So that's what TSNE really does. Where PCA fails, TSNE comes in handy and does these operations, and you can clearly draw a boundary between this. You can use k-means and knn for this particular algorithm. So another important thing, so plot difference between PCA and TSNE. I found this really cool image from Google. Like this is a world map. When you plot it in 3D, it looks like this. You can like make out some shape from this data. And after applying TSNE for that world map, this is how a model looks like to the PCA of that particular model. So you can clearly see that PCA follows a linear pattern. You can mark a boundary between all those classifications. It follows a linear pattern, whereas TSNE is a little bit chaotic. So it is easier to draw boundaries between them. So that's why we use TSNE for non-linear problems, and we use PCA for linear problems. So that's it for dimensionality reduction. So these are highly complex concepts. To explain each and every concept is just beyond the scope for this particular session. But this is just a basic idea of what really happens for this particular for these 2 particular algorithms. Any questions I would like to take? Any questions? Any doubts I should clarify?
Sir, in which scenario, like TSNE or support vector machine? Which one will be better, like scenario wise?
Yeah. Scenario wise, that's what I said. Support vector machine, you use it for supervised learning. Supervised learning means you know what the output value is going to be. So you train the model with the output value and predict it later on. So under those circumstances, you can use SVM. When you have when your problem is unsupervised meaning you don't know what the output variable is going to be, but you want to reduce the dimensions and draw the margins, you can use TSNE. TSNE is not a machine learning algorithm you use for prediction. It's just reducing the dimensions. SVM is a machine learning algorithm. This is not. This is like reducing the dimensions. So after applying TSNE, you can use SVM. You get my point? You don't use TSNE for prediction. You use is to reduce dimensions. So after applying TSNE, you can go ahead and use SVM, or you can use k nearest neighbors, which is also a machine learning algorithm, or use random forest or decision trees, any of your choice according to the dataset. TSNE and PC are just dimensionality reduction techniques that you use. These are complex techniques.
Okay.
So any doubt? Any other doubt? Sir, please send this. Okay. Okay, can I move on? I have another real life project I did for me to explain to you, which involves all these concepts I have specified in this particular session. Can I go ahead and explain those concepts? Explain my project?
Yeah.
Before
Yes,
that, any other doubts regarding this whole data pre-processing techniques that I've specified here, and thought you guys like how each and every step we can proceed? Any clarification should be made? Okay, I'll be moving on to my project explanation. Just give me a few seconds. Drink water. So I did a project on NASA turbofan RUL predictor. RUL is nothing but remaining useful life of a turbofan. Turbofan is nothing but a component of NASA's rocket, which is used to deploy satellites into space. So that particular rocket, so each rocket has a turbofan, and we need to identify the remaining useful life of this turbofan. So this whole problem comes under a category called predictive maintenance. So we're predicting the amount of useful life a particular problem has and maintaining it for better, for reducing the cost for that particular machine and get valuable results. So that's what predictive maintenance means. So for this, I've used NASA's dataset, which is available on Kaggle, which is for free. NASA was kind enough to offer this dataset because predictive maintenance is like true to one engine. It is like confidential to one company. So getting this predictive maintenance data is quite really tough job. So NASA has provided that, and it's in Kaggle. And for this visualizations, I have used Plotly. Plotly is another good function. I mean, good library to use for visualization purposes, and I also use Seaborn for this. So initially, I import this basic libraries: NumPy, Pandas, Matplotlib, Plotly, Seaborn. So the columns we have a lot of columns, including the ID. We have like 26 or 27 columns. So cycle representing, so one cycle represents one round trip. Two cycle represents two round trip. So two space to and fro, two space to back home. So one cycle represents one round trip. Operational 1, operational 2, operation 3 is the operational sensors. This 3 corresponds to all the other 23 sensors that we are having right now in this data set. So I am importing all the CSVs and reading it into a data frame. So train data frame, test data frame, and results data frame. So this results data frame contains the remaining useful life for that for the test data. So we'll be using these two data sets. So before diving on to pre-processing and exploratory data analysis, let's take a look at the data and amount of null values we have. So we have a total of 20,631 records, and we have like 0 null values, which is good. And except for sensor 22 and 23, these two sensors have zero data, that means the whole column is full of null values. We'll be dropping it later. It's safe to drop because we have nothing to provide. So we'll drop these two variables and we get the total number of null values. So as I said here earlier, sensor 22 and 23 have like zero data. We'll be dropping them. So initial insights, how the data is distributed. So the key things to look for is the mean and standard deviation for each particular column. So for each column, we have like the mean to be 51, 108, like 5.1 and 100, 1590. So 1408. All the mean values are like differently scaled or on a different scale. So we'll be seeing looking into that, and we have standard deviation also. So key things to look for. And before jumping on, let's see the correlation between the independent variables. So we need to drop those variables. So that's why I said like feature selection and feature elimination. So these steps, so those steps like come before even explorative data analysis. So that's what I'm doing here. So I'm plotting a correlation matrix using Seaborn heat map, and you can clearly see that sensor 18 and 19 have like a lot of correlations between them. So we need to drop 18 and 19 because it's like having twins in a data set. Having twins in a data set meaning it's going to create extra complexities, but returns the same results. So it's safe to drop these two variables and keep just one of them. Operational 3 has also a lot of correlation between them. And as I said, 22 and 23 also is safe to drop those variables. So that's what I've did here. So from this matrix, I have like eliminated 4 of these features at hand. And let's do the same thing for test also. Let's check the null values for test data set. We have like 13,000 entries for test data, and we'll check the results, the data set for results. And this is how a train data looks like. ID cycle, operation 1, operation 2, operation 3, and all the other 23 sensors. So first, I would like to identify the ID. So ID meaning one meaning one for classifying one engine. So I would like to get how many IDs I have in this data set. For that, we can use unique function provided by Python. And a quick run through the syntax gives us that we have over 100 engines for this particular data set. So we have 100 turbofan engines, and we have recorded each cycle for each particular engine. So that's what I've specified here. Quick inference reveals that there are 100 turbofans in this data. And let's plot the engine life cycle lifetime for each of those ID. So that's what I did here. Used dark background. I grouped the ID into one and got the cycle and got the max value for each of those ID cycle. And bar h is nothing but bar plot horizontal wise, and width is nothing but the width of this bar and all those other stuffs. Title xtext is nothing but the size or font of those labels, and I've plotted it. So this is what it looks like for train data. So for engine ID 1, the cycle lifetime is going to be about 180, I suppose 192 or 180. So after 192 cycles, engine 1 is going to fail. So after like 270 cycles, engine 2 is going to fail. So this is like completely supervised learning. We have recorded values. So that's what I'm visualizing here. You can see I visualize for all the 100 engines. And the next comes the pre-processing and feature engineering, as I already specified to you. What I'm going to do right now is that initially I'm going to drop the null values for the results data set, because you can clearly see there's a null column here in this data. So we'll be dropping those because we'll not be needing that. That's a data error. And instead of that, we'll be filling that with the index or the ID. So each record corresponds to the ID of each engine. So meaning first engine's remaining useful life is 112 after the inferences gained from the test data. So this results data is in correspondence with the test data. So I did the same thing for test data also. Test.group by cycle got the max value, reset the index, and I used that because I don't need remaining useful life right now. So I got the max value for each ID. So max value meaning remaining useful life that I'm going to have for that engine, so 3149. So that goes on for other 100 engines. So what I'm going to do right now is that I'm going to feature engineer a new column called remaining useful life failed. That meaning how much life it has after how much life it has for failing. So I got the results 112 for first ID, and I got the max cycle for that particular record, and I'm going to add those two and get the result. So 112 plus 30 is going to give me 31. In this case 31 is going to give me 143. So I've created a threshold for the failing circumstances for that particular cycle. So we're going to be using this feature engineered value for our model building. And right now we don't need, as I've engineered a new feature, we will not be needing the remaining useful life since we got the threshold value. So I've dropped that RUL access equal to 1 meaning column, specifying the column, drop the RUL column. In place is equal to true meaning, as I specified earlier. It transcends the change, transcends completely into the original data set. So there's no going back. And now the shape is going to be between 100 records and 2 columns. And the next step I'm doing right now is that I'm merging these 2 data frames. I'm merging test data and results data on ID, considering the left data set. So I'm merging the results column on the test data set. So this is like left join, inner left join. In SQL you might have come across. This is what I've done, inner left join for this. I got the values. So you can clearly see that with this data I've added the RUL failed also. So for each ID, it's going to be 143 for ID 1, and it's going to be 147 for ID 2. So likewise, it's going to be going on. And like I said, sensor 22 and 23 have full of null values, so I'm going to be dropping them. And in place is equal to true specifies already that it will be transcending to the original data frame. And since I've like dropped this also, I'll be also dropping the RUL failed in the test data set also. Now this null values, so we can see that we have a clean data, we don't have any missing values. Now we can go about and do the other things. So we have 0 null values in the train data, and we have 0 null values in the test data also. So what I'm going to do right now is that as each cycle has a threshold of 143, for this training data it has 192. So because I've done the same thing for train data also, what I did right here, I applied the same concepts I applied for test data to train data also. So what I'm going to do right now is that I'm going to subtract this remaining cycle value from the cycle value which is being recorded. So for the first cycle we have 192. After second cycle is going to be 190. So we'll subtract the cycle values from the remaining cycle. So for each count, it's going to the remaining cycle is going to reduce. Now let's visualize. I haven't done it yet. I've just explained. Now let's visualize, and later I'll be explaining and doing this concept. Visualizing the operational sensor's behavior. So let's visualize what each operational sensor reacts to each of those columns we have specified over here. So this is a big function I've used Plotly for that, and you can see for operational 1, and x-axis represents the cycle. Y-axis represents the sensor's value for each column value. We have like plotting for all the 100 engines in this one particular plot. So we have like a lot of variance between them is happening. So that means this data in this feature brings a lot to the table, and we can gain a lot of conclusions from this particular feature. And that same thing applies to operational sensor 2 also. And operational sensor 3 has a flat line, meaning that this doesn't bring anything to the table, or changes in operational sensor 3 doesn't affect the target value. So I'll be dropping operational sensor 3. Same goes for sensor 1, sensor 10. So this is like more like feature elimination and feature selection. That's what's happening here. I'm feature selecting and eliminating some of the features that I don't need just from EDA. Operational sensor 3, sensor 1, sensor 10, and sensor 11, 12 is good. Sensor 13 is also good. 14, 15 is good. 16 not needed since it's a flat line. Sensor 18 also not needed. Sensor 19 not needed. 2, 20, 21 have a lot of values it brings to the table, and these values corresponds to the output variable. Sensor 4 also. Sensor 5 doesn't bring anything. So likewise I have plotted for everything, and from this plot I can safely say that there are a lot of variables that we can remove. So for example, operator 3, sensor 1, sensor 5, and other important variables I'll be removing. But to be even sure, to make this even sure, if I'm dropping the correct variables or not, I'll be plotting another type of visualization called pair plot. You'll be seeing that in a moment. So this is nothing but visualizing the sensor recording of one single engine. So previously we had visualization for all the 100 engines. This is just for clarity purposes. I did for just one particular engine. So for engine ID 24, we plotted the values for each of those operational sensors. So they say it yields the same results, but just it gives more clarity. Another thing, to predict the cycle lifetime, I have created a threshold. So after each cycle, if that particular engine, the remaining useful life, comes before 30, after prediction, if it specifies 29 and 30, it's gonna classify it as 1, and it's gonna notify the concerned person or the maintenance person that this engine is gonna fail in 29 cycles or 28 cycles. So what this really does is that while it specifies that this engine is gonna fail in 28 or 29 cycles, to be precise, the respective person or the maintenance engineer can go ahead and repair this model, or you can decide on whether you can it is safe to fly the model or it needs checking or not. So that's the main solution that we are trying to offer here. So that's what I did. So threshold 30, it could be any value. Your threshold is not supposed to be 30. I mean, there's not a constant value or blueprint for setting this particular threshold. It could be anything, 35 or 40 or any other you like. But for safety purposes, for general purposes, I have set 30. So that's what I'm trying to do here. Label, creating a label, and for the remaining cycle, if it's below 30, I'm going to classify it as 1. And if it's above 0, if it's above 30, I'm going to classify it as 0. So that's what I've created here. And as I said, I'm using pair plot to further intensify my visualizations, because I had to be sure if I'm dropping the right variables or not. And hope you can see this color. So this is a pair plot. A pair plot happens between all those values according to those 3 sensors, operational 1, operational 2, and operational 3. With these features as the pillar, we have plotted scatter plot for each of those columns, up until sensor 1 till sensor 22. So this is a plot. So we can see that operation 1, operation 2, operation 3, and for all the 20 sensors. You can see that this sensor 1 has flat lines and it's safe to drop. As I said earlier, sensor 2, sensor 3, sensor 4 have a lot of variables and a lot of information. It contains a lot of information. Sensor 5, no, we can drop these variables. Sensor 6, we can drop. Sensor 7, 8 are good. Sensor 9 also good. Sensor 10, no need. So likewise, so if it has flat lines like it supposes in this operational sensor 3, so operational sensor 3 has full of one-dimensional value, so it doesn't bring any information, or changes in this variable doesn't affect the output variable. So we can drop operational sensor 3 and some of the variables which has flat lines. So after all these visualizations and understanding, I decided to drop these variables, which is going to be 1, 2, 3, 4, 5, 6, 7, 8. So we are dropping these 8 variables. So earlier we had 20, now we had 12. No, actually earlier we had 22, I suppose 22 or 23. Now we are having 12 or 13 variables. So we have reduced the variables, 10 variables. And I'm going to do the same thing for test also. So what I'm doing right now, since I've set a threshold, I'm converting that threshold value into this particular data set. So I've created this label. So 0 meaning it has a lot of life, and 1 meaning no, that particular engine is going to fail in another 28 cycles. So after considering these variables, I'm dropping them here. So x is equal to df train.drop. So I'm dropping all the variables I've specified and creating the input variables. And y is obviously the label output variable we have featured engineered. And the shape. So shape is the main thing. So input variables have a shape of 20,000 rows and 16 columns, whereas y has just 1 column, which are the labels, and 20,630 rows. Now let's move on to model building. So I've used train test split to split the training data between training data and test data. So I've used train test split from sklearn, and used 20% test size and 80% train size. which is going to give us 16,000 records for train and 4,000 records for test, and do the same thing for Y also. Y train 16,000, same thing, and Y test 4,127. So we have successfully split the data into training and test. So now we'll be supplying the train data to the classifier. So the next step, building the model. I've used LightGBM and XGBoost. LightGBM and XGBoost are libraries which we use to predict, or which uses random forest, gradiently boosted random forest methods for better model prediction. So these two libraries, which I'm gonna I have used in this data set, LightGBM and XGBoost, are way better than sklearn's random forest and decision trees. You can think of LightGBM and XGBoost has random forests and steroids. So that's like they give the maximum performance, and they're high speed. They're high speed random forests. So basically that's why I've used LightGBM and XGBoost. So you can install it in this PyPIY library. It's available for free. LightGBM is available for free. It's open source. And I've imported that classifier, LightGBM classifier. Learning rate I've specified to be 0.01. And estimator is nothing but the number of trees. So 5,000 trees is going to get the votes from 5,000 trees and get the maximum vote to be the predicted value. Number of leaves is nothing but the depth of the tree. Objective binary. So we have a binary classification problem here, as I specified, because we have to classify between 0 or 1. So it's binary classification problem. So our objective is going to be binary. Metrics is accuracy, and random state also I already told you. It's just a seed, nothing much. And I have used the parameters extend and weighted on this light classifier and I fit this model and get the score and predict this model from X-test and get those values and store it in PREDS data. And later I am printing out all the scores. So accuracy score I'm printing out. ROC is nothing but area under the curve for a score for this precision recall curve. And we have like precision score, recall score, and F1 score. F1 score is nothing but precision score and recall score combined. So we get an accuracy of 0.96, which is nothing but 96% specified here, and ROC accuracy score of 0.91, 91%. Precision is good, 90. Recall is a little bit down, 83%, and F1 score is 86. So this model is currently performing quite okay, but we need to do a lot of hyperparameter tuning for this model to perform better. And this is like, since I have explained this in the data preprocessing session, that feature importances, we can gain the knowledge of feature importances, how much each feature is bringing to the table. So the change in each feature or each column, how much it translates into the output variable. So that's what I'm trying to do here, because LightGBM offers this feature importances function. So using that, I'm plotting the bar chart for each features that we use in this data. So sensor 15 is important. So we can take the top 5, sensor 15, 14, 3, 21, 2 are all like bring a lot to the table, holds a lot of information. That means that changes in these features affects the output variable. So that's what it specifies here. If you want, you can go ahead and drop sensor 17 and operational 2 also if you need. But right now I'm keeping it since it is a research session. And next thing, this, as I said, this depicts the weightage of the important variables. Here I've used LightGBM. Now let's use XGBoost and compare these two libraries. What results do these two classifiers provide? And for this particular library, I've used stratified k-fold and randomized search CV, and I imported XGBoost as XGB. So stratified k-fold is nothing but we use this type of function when you have an imbalanced data set. Right now we have an imbalanced data set because we have like 85% 0 and 15% 1. So if you like train a model right off the bat, it is going to get biased and try to classify each and every record you put into the model as 0. Our accuracy is going to increase, but accuracy is going to get increased, but our recall score is going to get damaged, because since our model gets biased so much, it doesn't consider labeling that record as particular record as 1 or 0. So it records, it predicts each and every record as 0. So under those circumstances, when we have imbalanced data set, we use stratified k-fold. So n split is equal to 5 means split this data into 5, and each split contains the same amount of weightage that we have between 0 to 1, or the ratio between 0 to 1 label. The same amount of ratio is maintained when the split is happening. So we preserve the information, there is no information loss. And I've imported XGB classifier and estimated 750, meaning that we're going to use 750 decision trees or random forest, or naturally uses random forest, and 750 is the number of trees. And this dictionary is for my randomized search CV. So I'm going to arrange. This is also called as hyperparameter tuning. So for each of those parameters, we have like learning rate, max depth, min child weight. So for each parameters, we're gonna set a range and the value of the step of the range it should take for each iteration. So combining all of those and considering all those values, our model and take all these values and train the model. And after training so much of models, randomized search CV is going to get the parameters which produce the best results or the maximum accuracy score. So that's what I did here. Imported the randomized search CV, imported the classified and fit into that parameter. CV cross validation is nothing but stratified k-fold, and I fit that model. So I use X-train and White and naturally, and let's see the score. So we have increased our score has been decreased on the training test set from 96 to 95, but our recall and precision are actually higher than light GPM. So yeah, our XGBoost got 95% on validation data set. Now let's check the best parameters it provides. So for this particular accuracy to get, these are the parameters we should be using. So that's what it's specified. That's what randomized search CV gives you. And let's predict the prediction that the classifier, using that classifier, let's predict the test data for that particular problem we had on our hand. Remaining cycle and label obviously. And let's plot the confusion matrix also. So after training the model on XGB, and we got the accuracy score to be 98%. So we have increased from 96 to 98 on this particular using this particular classification model. So let's plot the confusion matrix. Confusion matrix is nothing but the x-axis is the predicted. The x-axis is the actual values and y is the predicted values. So when this particular column represents the actual number of zeros. So 12,614 plus 78 is the total number of zero values we have, and our model predicted it to be 12,614 times. So that goes, the exact same concept goes for 1 also. So this is the actual values, 254 plus 150, and out of those actual predicted values, our model got 254 of them right. So our precision is extremely good, but our recall is a little bit less. We already saw our recall is 83% because our model got biased. Even after using stratified k-fold and using randomized search CV, model still got biased because the amount of ratio we have between 0 and 1 is like huge, because 0 has 85% and 1 has only 15% of the data. So it's bound to happen. If you want to increase the recall score, we can collect a lot more data. So we can collect a lot more data which has the labels 1. So we can reduce the score. We can reduce the error, and we can increase the recall score. So this is the best parameter I've used, and we got the best results from using these parameters. And now the next step is saving the model. So there's a package called Pickle, and we use Pickle to save this estimator, and this is going to be saved in a Pickle file. And later we can use this Pickle file and give this to a domain expert or web developer so that they can integrate this particular model into their web application or some sort of stuff. So this is just for my validation purposes, how it's performing after importing the data. So because I have saved this model into a Pickle file, I've again imported it and saved it into a model variable, and I'm checking it on the validation data set. So before predicting, I'm checking the values for the first 10 values, and I'm predicting it to be for the first 10 of the X-test data set. So out of those 10 values, our model got all the 10 values to be correct. So for this particular problem, we have like 100% accuracy. So this is the end of this project. Any doubts I can clarify? So the basic idea is that this is a predictive maintenance problem for which I have used solution of binary classification. So any questions regarding this project?
That's a lot of work you have done, Sashank.
Thank you so much. So any questions I can clarify, any doubts or any comments? Let me check. Yeah, okay. Sure, sorry, I'll share the GitHub link right now.
Sir, do you have any idea about the feature selection?
Sorry, come again.
Feature selection. You talked about feature engineering.
Yeah, feature. Yeah, okay.
Similarly, something called a feature selection is there.
Yeah. So let me explain. So
the picking up the very important features.
Yeah. So that's what I've done here. Feature selection. Right now, for feature selection involves process of selecting features from exploratory data analysis. That's what I said. Feature selection is like different for each type of data. So that's what I've done here. I've plotted some of these values against each of these operational sensors, and you can clearly see these flat lines, right? Operational sensor 3 has a flat line, sensor 1 has a flat line, sensor 10 has a flat line. So we can feature eliminate these 3 values and select these other values which holds a lot of information. So this is called feature elimination and feature selection. So there are three types of classifications I did here. One is plot like this, another is a heat map I did, also known as correlation map at the starting.
Yes.
So this is also a form of feature selection and feature selection and feature elimination, and a pair plot. That's what I've done here. So this is also a form of feature selection and elimination. So from these 3 visualizations, I came to a conclusion that I can drop these specified 8 variables. So this is like feature elimination, and I've selected these other features, excluding these all features. Is it clear?
Okay, sir. After eliminating, removing the unimportant features, you tested the accuracy also.
Yeah, I tested the accuracy. So it obviously increased. We have reduced the complexity of the problem also.
Yes.
Previously, we had like 24 variables, I suppose so. Right now, we have only 12 variables. And we have eliminated those 10 variables. We have like reduced the dimension of those variables. The data set, actually. Let me share my GitHub.
Will you share this notebook, sir?
Yeah, I'm sharing right now.
Okay, sir. Thank you, sir. Nice session, sir.
Thank you so much. So I've shared my GitHub profile. Right now, the notebook I presented to you right now has a lot of changes from that particular notebook in GitHub. I'll update my notebook by today evening. So you'll have the updated notebook. Because after uploading, I did a lot of changes in those data and a lot of changes in this notebook. So I'll try to update the notebook by today evening, like 6 or 7, I suppose. But 95% of the information is already in that notebook. It's in GitHub. So any doubts you have regarding this session? Thank you so much. Thanks a lot.
Thank you, Sashank. And
Thanks a lot, sir, for your new words. You have clarified well.
Thank you so much. I hope I've satisfied your expectations. I hope you gained a lot of information from the session.
Heartfelt thanks to you, sir. A very nice explanation, data cleansing, data pre-processing concepts with a hands-on project. Thank you very much, sir.
Yeah, thank you so much.
Thank you.
I'll stop sharing.
It was fine.
Thank you so much. Thank you so much.
Thank you, Sashank. That was indeed a wonderful session.
So can you provide us your phone number?
My phone number.
Phone number and mail ID.
So just a second. I'm putting it. So this is my phone number.